Okay, so now let's have the application of galvanic cells. So we have battery. So it is a galvanic cell, or more commonly, a group of galvanic cells connected in series, where the potentials of the individual cells added to give the total battery potential. So batteries are a source of direct current and have become an essential source of portable power in our society. So the common type of battery is lead storage battery. So since about 1915, when self-starters were first used in automobiles, the lead storage battery has been a major factor in making the automotive a practical means of transportation. This type of battery can function for several years under temperature extreme from -30°F to 120°F, and under incessant punishment from rough roads. So, in this battery, lead serves as the anode, and lead coated with lead dioxide serve as the cathode. So, both electrons dip into an electrolyte solution of sulfuric acid. So, electrolyte is a solution that allows the, the passage or the flow of electrons. So it can be liquid or solid. So a typical automobile lead storage battery has a 6 cell connected in series. So each cell contains multiple electrodes in the form of grids, as you can see in the figure. And it produces approximately 2 volts for each cell. So it gives a total battery potentials of about 12 volts. Dry cell batteries. So the calculators, electronics games, digital watches, and portable CDs players are just some familiar to us. And it all powered by these small, efficient batteries. The common dry cell batteries was invented more than 100 years ago by Georges Lanclache, a French chemist. So in its acid version, the dry cell battery contains a zinc inner case that acts as the anode, and a carbon rod in contact with the moist phase of solid manganese oxide, solid NH4Cl, and carbon that acts as the cathode. So this moist phase is the electrolytes in solid form. So the half reaction are complex but can be approximately as follows. So this cell produces a potential of about 1.5 volts. For an alkaline version of this dry cell battery, the solid NH4Cl is replaced by KOH or sometimes NaOH. So in this case, the half reaction can be approximated as follows. And the alkaline dry cell lasts longer mainly because the zinc anode corrodes less rapidly under basic conditions than other acidic conditions. So the other type of useful batteries includes the silver cell, which is presented in the figure, which has a zinc anode and a cathode that employs Ag2O as the oxidizing agent in a basic environment, while mercury cell has a zinc anode and a cathode involving HgO as the oxidizing agent in the basic medium. So see at the figure the diagram or illustration of a mercury cells. Another important type of battery is nickel-cadmium battery, in which the electrons reactions as follows. So just like lead storage battery, this nickel-cadmium battery can be recharged an indefinite number of times. Another application of galvanic cell is a fuel cell. So it is a galvanic cell for which the reactants are continually supplied. To illustrate the principles of fuel cell, let's consider the exothermic redox reaction of methane with oxygen. So CH4 or methane plus 2O oxygen, arrow CO2 plus water plus the energy that being harnessed from this reaction. So usually the energy from this reaction is released as heat to warm houses and to run machines. However, in a fuel cell designed to use this reaction, the energy is used to produce an electric current. The electrons flow from the reducing agent, methane, to the oxidizing agent through a conductor. Another application of this fuel cell is the US space program, which has supported extensive research to develop fuel cells. So the space shuttle uses a fuel cell based on the reaction of hydrogen and oxygen to form water. So a schematic of a fuel cell that employs this reaction is shown in the picture at the right side. So fuel cells are also finding use as a permanent power source. For example, a power plant built in New York City contains stacks of hydrogen-oxygen fuel cells, which can be rapidly put online in response to fluctuating power demands. The hydrogen gas is obtained by decomposing the methane in natural gas. A plant of this type also have been constructed in Tokyo. In addition, new fuel cells are under development that can be used fuels such as methane and diesel directly without having to produce hydrogen first. Corrosion can be viewed as a process of returning metals to their natural state, the ores from which they were originally obtained. So this corrosion involves oxidation of the metal. So since corroded metal often loses its structural integrity and attractiveness, this spontaneous process has great economic impact. Approximately one-fifth of the iron and steel produced annually is used to replace rusted metal. So in the figure, we can see that the iron dissolves, forming a pit, which acts as the anodic area or the anode, and the rust is served as the cathode area or cathodic area. So metal corrodes because they oxide easily, except for gold. Those metals commonly used for structural and decorative purposes all have standard reduction potentials, less positive than that of oxygen gas. When any of these half reactions is reversed to show oxidation of the metal and combined with the reduction half reaction for oxygen, the result is a positive standard reduction potential value. Thus, the oxidation of most metals by oxygen is spontaneous, although cannot tell from the potential how fast it will occur. The corrosion products of noble metals such as copper, silver are complex and affect the use of these metals as decorative materials. So under normal atmospheric conditions, copper forms an external layer of greenish copper carbonate called patina, while silver tarnish is silver sulfide, which is thin layer gives the silver surface a richer appearance. Gold with a positive standard reduction potential of 1.5 voltage, significantly larger than that of oxygen, which is 1.23 volts, show no appreciable corrosion in air. So here are the following ways to prevent corrosion. So prevention of corrosion is an important way of conserving our natural resources of energy and metals, and also money. The primary means of protection is the application of coating, most commonly paint or metal plating, to protect the metal from oxygen and moisture. So we have chromium and tin are often used to plate steel because they oxidize to form a durable, effective oxide coating. Also, we have zinc, also used as a coat steel, which the process is called galvanizing to form a mixed oxide carbonate coating. So next way to prevent corrosion is alloying. So stainless steel contains chromium and nickel, both of which form oxide coating that change steel's reduction potential to one characteristic of a noble metal. In addition, a new technology is now being developed to create surface alloys. That is, instead of forming a metal alloy such as stainless steels, which has the same composition throughout, cheaper carbon steel is treated by ion bombardment to produce a thin layer of stainless steel or other desirable alloy on the surface. So in this process, a plasma or ion gas of the alloying ions is formed at high temperatures and is then directed onto the surface of the metal. So last prevention for corrosion is cathodic protection. So it's a method most often employed to protect steel in buried fuel tanks and pipelines. An active metal such as magnesium is connected by a wire to the pipeline or tank to be protected. Because the magnesium is a better reducing agent than iron, electrons are varnished by the magnesium rather than by the iron, keeping the iron from being oxidized. As oxidation occurs, the magnesium anode dissolves, and so it must be replaced periodically. Ship's hulls are protected in a similar way by attaching bars of titanium metal to the steel hull. In salt water, the titanium acts as the anode and is oxidized instead of the steel hulls, the cathode. So let's have you check your understanding how our batteries and fuel cells are alike and how are they different.